Bob briefly. He's a Ronald P. and Susan E. Lynch Professor of Investment Management at Cornell University. Bob is he is very well known for the HJM model that came out in 1992, and I remember I got my PhD in 1990, and that was the hottest model at the time. And this kind of ties into the presentation by Emmanuel, and it was kind of an extension of that research, which began with Thomas O. And then we had Black-Merton-Scholes model, and then Bob really extended that to multiple factors, and the HGM model is used even today in a lot of the central banks and in these areas. He also invented the credit risk model, which is kind of a standard model used in the industry. He co-created the journal Mathematical Finance, and he's an advisory or associate editor for numerous other finance journals. Let me speak a little bit about the number of awards he's won. He has won the Graham and Dodd-Scholes Award in 2001, the CBOE Pomerantz Prize in 1982, the Ross Best Paper Award in 2008. And in 1997, he was the IAFE Financial Engineer of the Year in recognition of his research accomplishments. He's in the Fixed Income Analyst Society Hall of Fame, Risk Magazine's 50-member Hall of Fame, and listed in the Who's Who of Economics. He received Risk Magazine's Lifetime Achievement Award in 2009, and he serves on various corporate boards and advisory boards. So Bob, the floor is yours. Bob is going to talk about the last 50 years of arbitrage pricing using Black-Merton-Scholes. So all yours, Bob.
Thank you for the generous introduction. Perhaps something many don't know, I studied option pricing theory under Bob Merton and Fisher Black when I at MIT to obtain my PhD, and that experience created my lifelong interest in derivative pricing theory and practice. Now I'm going to share my slides, and I'm hoping everybody, it says everybody can see my slides. Okay.
Yes.
Excellent. All right, so I'm going to work through these, and I have about 45 minutes or so, maybe a little longer.
Yes.
And as was stated, I'm going to talk about arbitrage pricing theory over the past 50 years. And geez, it's hard to believe it's been 50 years. But it has, and we've learned an awful lot. So first I'm going to review the Black-Merton-Scholes model. Then I'm going to talk about what are called the fundamental theorems of asset pricing, the extensions of the Black-Merton-Scholes model, and they're listed in blue here: alternative risky asset price evolutions, the HJM model, the reduced form credit risk model, frictions, incomplete markets, and non-competitive markets. The key insight, the key takeaway from the review is that the BMS methodology is very robust to modifying all of its assumptions, except perhaps for the relaxation of the competitive market assumption. And we'll understand why and get into this later. So the Black-Merton-Scholes model planted a seed. The seed grew into a massive tree with strong roots over the past 50 years. And I think of the roots as the formal mathematical foundations. These are the fundamental theorems characterizing the notions of no arbitrage in complete markets. And of course, complete markets is the idea of replication. The trunk and branches correspond to the extensions and applications. Today, I'm really only going to talk about the roots, the foundations, the extensions, the trunk and branches, but not the applications. In fact, there's too many to do in an hour presentation. Now, to save time, the references and the authors of the extensions that I talk about below are omitted. However, a complete listing of these are in my recent textbook, which I give here in case anyone is interested in, looking up the details. All right, The C, the BMS model. A model is characterized by its assumptions, so I'm really going to emphasize the assumptions and then subsequently the implications. As we can see here, there are 6 assumptions. Now, I'm not going to, those assumptions that are quite common and well understood, I'll just mention them. And I won't go into a deeper explanation of what the assumption means. So we have competitive markets, frictionless markets, continuous time and continuous trading. The emphasis is continuous trading, and the notion of no arbitrage. The original model assumed constant interest rates. So given here, B sub t is the value of a money market account at time little t, and R is the spot rate of interest, sometimes called the riskless rate. Assume that the stock price process follows geometric Brownian motion, where the drift and volatility parameters are constants. And typically we assume no cash flows on the underlying stock, but that is easily relaxed. Merton, whose paper was published in the same year, extended the Black-Scholes assumptions in 2 ways. He modified the constant interest rate assumption and included trading in a default-free bond that matures on the maturity date of the option. Also the geometric Brownian motion, it could have a stochastic drift and a deterministic volatility. And of course, he necessarily maintained no arbitrage, the no arbitrage assumption. The implications, and we're looking at a European call option with maturity T and strike K on the stock. The key one of the 2 key implications was, and has later become known as risk neutral valuation, that the value of the option is equal to the expected discounted payoff, where the expectation is taken with respect to what's sometimes called the risk neutral probability measure. And here I call it the martingale probability measure, and that's represented by Q in the expression. When you do the compute the expectation, you get the famous Black-Merton-Scholes formula, and it's given here, of course, and that's one of the key implications. The second, and in my view, the most important implication is dynamic replication. One can show there exists a dynamic trading strategy that replicates the options payoffs. I personally call that synthetic construction. And why do I think it's a key insight? Because that's the theme that enables one to develop the subsequent extensions that I'm going to talk about. And the trading strategy is the holdings in the underlying stock is equal to what's called the hedge ratio, which is the option price's partial derivative with respect to the underlying stock price. I mean, of course, all of these results are well known, and I'm just reviewing the model because I want to emphasize modifications of the structure and subsequent modifications of the implications. All right. So what are the limitations of Black-Merton-Scholes? Well, this is true of any model. A model is limited in its application to the extent that the assumptions are good first approximations. And the key ones underlying Black-Merton-Scholes are very active in liquid markets, so nearly frictionless and competitive. And crucial in the model structure is that there's only a finite number of assets trading. And here with price processes whose volatilities are constant or deterministic. All right. It's clear the needed extensions, therefore, are going to be for markets where those structures are not good approximations. And I just have a list here of the types of structures which, well, what can go wrong? Volatilities are often stochastic. prices may exhibit jumps, and there are term structures of prices, for example, of interest rates, which is an infinite number of assets, not a finite number. There are transactions costs, sometimes they're large enough to make a difference, and trading constraints sometimes exist. And last, trades in less liquid markets can affect the price paid or received. And all of those are significant departures from the Black-Merton-Scholes assumptions. So we need to understand, is the theory robust to a relaxation of these? And the way I'm going to proceed is I'm going to talk about each of the assumptions separately and sequentially, and not necessarily chronologically. All right. And of course, in practice, oftentimes you're going to have to join together one or more of the modifications to get a model for a particular application that's a closer approximation. But before I go to the extensions, we're going to step back and discuss the foundations of arbitrage pricing theory. Again, what I think of as the roots. Now, here are the basic assumptions, right? Competitive markets, frictionless markets, continuous time and continuous trading. We need to introduce some terminology for the randomness that characterizes the randomness in the market. And key in this characterization is what's called the statistical probability measure, P. And that's the objective measure, which we can think of an omniscient being drawing from a very large urn the price processes that we see. There's assumed a finite number of semi-martingale asset price processes. S will denote a vector of risky asset prices, and B will be, as before, the value of a money market account. And the semi-martingale characteristic of the price process is very general. I'll mention it again later, but it allows discontinuous sample path processes. Trading strategies, trading in these risky assets and money market account across time need to satisfy measurability conditions. You can't look to the future to decide what to trade today. Typically, we study self-financing trading strategies, no cash inflows or outflows, because it makes the analytics simpler. However, it's not really necessary. And we also require that our trading strategies are what are called admissible, which means the value of the trading strategy can never get too large negative number. So that is, if you lose too much, at some point you can't borrow anymore. And this condition is included to reduce doubling strategies, which would exist in a continuous trading model without the inclusion of such a restriction. And it turns out that it's this restriction, the admissibility condition, that creates a phenomenon in these models which can exist, and I'll talk about them later, but they're called asset price bubbles. But that's the genesis of the possibility of asset price bubbles in asset pricing theory. So some definitions, some of these you're probably very familiar with. I'll just go quickly. No arbitrage, right? We typically call that simple arbitrage. And then we have an extension, which is an approximate arbitrage opportunity, which has the acronym NFLVR, no free lunch and vanishing risk. No dominance, introduced by Bob Merton in his 1973 paper. Here, it just means that no assets payoffs can be obtained at a lower initial cost using an admissible self-financing trading strategy. And then the notion of complete markets or synthetic replication. And for this definition, you really have to specify a probability measure. But given such a measure, I'm going to stay away from the details for a moment until they become important. That given a derivative's payoffs, there's And there exists an admissible self-financing trading strategy whose value process replicates the payoff to the derivative and is a Q martingale. All right. Of course, the mathematical foundations are very technical. And I've only got an hour, so I'm skipping over a lot of subtle details, but I'm hoping this will be without loss of overall understanding. So those are the four definitions. And here are the three theorems, which I call the fundamental theorems. Now, the first one is that NFLVR, which is no approximate arbitrage opportunities and no arbitrage opportunities. Market satisfies that if and only if there exists an equivalent local martingale measure. And a local martingale measure is a probability measure equivalent to P, such that the normalized risky asset price process is a local martingale. And a local martingale is something that is a weaker version of a martingale. Theorem 2, if you add the assumption of no dominance, then a market satisfies both NFL and no dominance if and only if there exists an equivalent martingale measure. All right, the distinction between local martingale and martingale is really characterized by the addition of no dominance to your market structure. And then for theorem 3, if we assume NFL, VR, and D, choose an equivalent martingale measure. And then the martingale measure, I'm sorry, there's a typo here. The market is complete with respect to Q if and only if the equivalent martingale measure is unique. All right, so you get uniqueness of a martingale measure when it exists, because we're assuming NFL, VR, and ND, if and only if it's unique. And it's these three theorems that characterize economic notions in mathematical formalism. And the mathematical formalism enables us to develop theorems and understand subtle structures. And there's an important corollary, which I call risk-neutral valuation, where we're basically going to assume NFL, VR, ND, and complete markets with respect to, now we know the unique E equivalent martingale measure. Then under those three assumptions, the time t price of any derivative with a payoff that is appropriately measurable and integrable satisfies the formula risk neutral valuation. You take its expected payoff, you discount at the stochastic spot rate of interest, and you get the value, the arbitrage free value of the derivative. And the arbitrage free value is actually the cost of construction. And that's hidden in the proof of this corollary. And I stated here, i.e. there exists a trading strategy such that the value process equals the xt for all t, and that's particular at time cap t, you get your replication. Now those are the fundamental theorems, and they enable us to get some deeper insights into the structure of this market, this hypothetical, this theoretical market, and therefore we can understand its implications and then compare the implications with actual markets to see whether or not it's a good approximation or not. And the one I mentioned earlier is asset price bubbles. In the generalization of the theory, the foundations, we actually realize that no arbitrage generalized only guarantees the existence of a local martingale measure. And if it's not a martingale, well, what does that mean? Well, it means that there exists what we call an asset price bubble. And that's the difference between the market price, which is ST over BT in the blue equation, minus the fundamental value, which is the expected discounted payoff from holding the asset until liquidation and not reselling it. That's basically the classical definition of a bubble. And so once we understand that bubbles can exist in these arbitrage-free models, then we want to understand, well, what type of market structures, what's a sufficient condition for excluding them? It turns out NFLVR and complete is not enough. They can exist, and that implies no dominance is violated. But if you add no dominance, if you add no dominance and you have a complete market, asset price bubbles cannot exist. All right. But if you have an incomplete market, then they pop up again. And it'll be, and I'll talk later about how we can price derivatives when there are asset price bubbles. And many practitioners and also academics do believe price bubbles exist. So this is a very important topic from my perspective to understand how the theory handles it. Now, going back to Black-Merton-Scholes, I just want to point out that the Black-Merton-Scholes evolution is consistent with NFOVR and ND. It does imply the existence of a martingale measure. It also implies the market's complete because you can do synthetic replication under geometric Brownian motion. Hence, by construction, the BMS option pricing model excludes asset price bubbles. So if you believe stock price bubbles exist, you can't use this model. All right. Okay, that's a lot. I'm moving fast here. So given this background, which are the foundations, we can now begin our journey and talk about extending the Black-Merton-Scholes model by relaxing each of the assumptions. And the first, so we're going to talk about the extensions. And the first one I'm going to talk about are alternative risky asset price evolutions. We actually already did this, but I'm going to repeat it because I went over it so quickly. So assumption number one is that we know the theory extends to asset price processes, which are called semi-martingales. But in the beginning, just a finite number, semi-martingale risky asset price processes. Very general. It includes as subcases, diffusions, plus jumps. This extension, you can have a finite number of default-free zero coupon bonds trading to handle stochastic interest rates. Although limited to in its application, it's still within this theory. And why semi-martingales? Well, because those processes are those for which stochastic intervals are well defined. And as I said before, examples include stochastic volatility and jump diffusion processes. Now, the extension to an infinite number of asset price processes, I'm going to discuss that below, and that's really the HJM model. All right. Of course, you're going to have to assume no arbitrage and no dominance, and that puts a restriction on the semi-martingale price processes, and we need those to get the existence of an equivalent martingale measure. You're going to have to assume complete markets. Again, that's really when you impose your structure on your asset price processes, has to do with the characteristics of that price process. We need that to get uniqueness of the equivalent martingale measure and the ability to do synthetic replication. Completeness really depends both on number of assets trading, the price process itself, and embedded in the price process, the number of martingale shocks that create the randomness as you evolve across time. And intuitively speaking, you need what's called martingale representation to hold for the randomness in the market, and that a subset of the assets have a one-to-one and onto transformation from the asset price evolution to the martingale processes randomness that they generate. That is, the randomness can be alternatively viewed, the randomness that generates the price processes can be alternatively viewed as the price processes themselves, okay? So that there's one-to-one, relationship between the two. And that ability to sort of do that means that you can create a trading strategy that'll replicate the payoff to randomness generated by the martingales, which are equivalent to the randomness generated by the stock prices themselves. And there's no extraneous randomness in the system. Well, if we don't assume complete markets, that is, if we don't impose enough structure on the price processes such that this is true, then you're in an incomplete market. And I'll talk about that later. So those are the three assumptions. Under those three assumptions, we get risk neutral valuation and we get synthetic replication. We also, in this framework, can better understand asset price bubbles. And as I mentioned before, there are basically two market structures where price bubbles can exist. One is a complete market where no dominance is violated. And the other is an incomplete market where you have no arbitrage and no dominance being satisfied. And this is a really quick overview, but in the first market, which is complete, you can actually show that there are buying holding in the stock is dominated by a dynamic trading strategy in the stocks, the risky assets and money market account. Which means that if you actually do believe the market has a bubble and it's approximately complete, that you never want to hold the stock itself as a buy and hold. There's a better way to get the same payoff on the stock by trading dynamically. Risk neutral valuation here typically fails for calls, but it does hold for puts, which is also interesting, and that's because puts have bounded payoffs. On calls, payoffs are unbounded above. So market one, we actually know an awful lot about the structure and how to handle the valuation and replication of derivatives in that structure. Market two, when you add incompleteness, but still make the market slightly nicer by adding no dominance, the fact that synthetic construction fails means that pricing is going to happen differently. You're going to be pricing in an incomplete market, and we'll be talking about how to do that later as well. But typically, well, there are some general rules. One is that risk neutral valuation again fails for calls when you're pricing in an incomplete market, but it does hold for puts. And that actual difference enables one to test for the existence of bubbles under market structure two, a topic for some subsequent discussion. All right, well, risky asset price processes, general semi-martingales, as long as you keep completeness and then a martingale measure exists, everything goes. All right, HJM, stochastic term structure of interest rate. What's really here the extension that's significant? That you have an infinite number of price processes trading which are correlated and related to each other. There's a term structure. And of course, the canonical example is on the term structure of interest rates. You have all of the assumptions, the top three are the same: competitive, frictionless markets, continuous time in trading. And then we impose an evolution on the term structure. And the key here is that you have a continuum. For this example, default-free zero coupon bonds. And you start with an initial term structure of forward rates. The spot rate is the forward rate for immediate, where the two arguments are the same. And you assume an evolution for the forward rate process. HJM introduced a D-factor model with Brownian motions given here, but it's easily generalized to include jumps. It's been generalized to include an infinite number of Brownian motions. Yeah, so it's been generalized in many ways. Given that structure, we need to impose conditions on the drifts and the volatilities such that it satisfies, no arbitrage and no dominance. And on the drifts, that's known as the HJM drift condition. And for complete markets, for the finite factor model, you basically need a non-singular volatility matrix for, a D element finite subset of the traded zero coupon bonds. But that gives us back all the assumptions, and structure enables us to use the corollary risk neutral valuation. And we have an expression for the price of a zero coupon bond as the expected discounted value of its payoff under the equivalent martingale measure. And any interest rate derivative, as long as the payoff is appropriately measurable and integrable, will satisfy risk neutral valuation. And we know, because the market's complete, you can synthetically construct its payoffs. I think of this as an advantage, but I've been, sometimes some scholars say it's a disadvantage, but from my point of view, the theory gives you multiple ways to replicate any derivative, and sometimes because of market frictions, if they're not too great, or liquidities, you may prefer one method of replication over another. Yeah, so, but that's an implication of the theory, because we have an infinite number of traded assets, but only a finite number of random shocks. Now, the HJM model itself has been extended and applied to other term structures, for example, foreign currency term structures with multiple foreign currencies, nominal and real term structures. We were talking about the nominal term structure here, but you can include real term structures and deal with inflation derivatives. The term structure of commodity futures prices, very important application. You can think of plain vanilla calls and puts. They have a term structure of strikes and maturities, which you can apply this technology to, and credit risky bonds, which I'm going to talk about next. And that takes us to the reduced form credit risk model, which I think of as an extension of HJM to allow for default risk. And although it was not previously stated, when you're talking about derivatives, and everything I've said before this, there was an implicit assumption of no counterparty risk when you're trading derivatives. Derivatives are in zero supply. For each long, there's a short. And for the payoffs that we specify to be valid, the other side of the contract must execute as promised. All right. Now, if they don't, then the payoffs are not as promised, and that's counterparty or default risk. And the credit risk model really is the relaxation of this no counterparty or no default risk assumptions. I'll briefly go through the modifications. As you can see here, HJM, all the assumptions of HJM you maintain. We introduce trading in the simplest setup, and these can be generalized. We introduce trading in a risky zero coupon bond promising to pay $1 at some future date T, and it's issued by some credit entity, a firm, a government, financial institution. We're going to let tau be the default time of the credit entity, and it's a stopping time. And if the credit entity defaults before the promised payment is made, we assume that the zero coupon bond pays a recovery rate of delta dollars as a percent per dollar owed. And then since it's the zero coupon bond, only promises 1. That's the percentage recovery rate. Of course, we're going to have to assume the structure on the evolution such that NFLVR, ND, and market completeness holds. And that's so we can invoke risk neutral valuation. We do that, and the existence of an equivalent martingale measure gives us formulas for both the default-free zero coupon bonds and the risky zero coupon bond. Given by those formulas, I'm not going to emphasize the formulas. And then, of course, given any credit risky derivatives, with appropriate payoffs, measurable and integrable, risk neutral valuation holds. Again, the cost of construction or the arbitrage-free price of the credit derivative is the expected discounted payoff using the equivalent martingale measure. And under the above structure, we can get synthetic construction. Now, using this methodology, we can easily price and hedge credit derivatives, examples, credit default swaps, coupon bonds with embedded options, and the list goes on and on and on. But there's a complication. There's a fly in the ointment, so to speak. Typically, when you build these price processes, the default time is what's called an inaccessible stopping time, which means it's a surprise. It's not anticipated, and the recovery rate is often a diffuse random variable, and the conjunction of those two typically implies the market's incomplete. All right, but we still would like to use risk neutral valuation if we could, but we're not going to be able to do synthetic replication if the market's incomplete. And there are two ways one can finesse this complication. One is to assume trading in the credit derivatives themselves, and the inclusion of them may then complete the market. And if that's true, then we get unique pricing, risk neutral valuation comes back alive, and synthetic construction works, but however, now you have to trade in the credit derivatives as well. Now, if that finesse doesn't work, then you're in an incomplete market. And I'll be talking about how you price in an incomplete market below. All right, so those were on the asset price processes. Now we go to frictions. Two types of frictions that I'm going to talk about: transactions costs and trading constraints. Now, for transactions costs themselves, there are basically two types. There's a fixed fee per trade, and there's a variable cost per unit traded. All right. Now, if the transactions costs are fixed per trade, then continuous trading is infeasible. Over any finite time interval with continuous trading, your transactions costs would be infinite. So it's completely infeasible. And which means that the model structure is then you're only going to be able to trade, and the most general version is on a finite number of stopping times over any finite interval. This is going to imply the market's incomplete, standard pricing and hedging fails, and we're going to have to move to incomplete markets structure for pricing, and I'll talk about that later. However, some good news: if it's variable cost per trade, then with continuous trading, if you trade quickly enough, so for example, high frequency traders, you can avoid these costs. It turns out with the standard pricing methodology, and the risk neutral valuation still approximately applies. And the reason I didn't go into the notion on the slide of a temporary quantity impact on the price is because this variable cost per trade are a special case of something called liquidity risk, which I'll talk about later. What about trading constraints? Well, trading constraints are a difficulty. For example, short sale restrictions. Again, here it makes the market incomplete, and the standard pricing and hedging methodology typically fails, which means that if you're going to deal with this extension, you have to understand how to price in an incomplete market. And that's where I'm going now. incomplete markets. All right, we want them to be nice, so we're going to assume NFLVR and ND. And of course, that means there exists an equivalent martingale measure. But we're going to assume the market's incomplete, so synthetic construction fails. Now, the fundamental theorems and the mathematics of that enables us to understand these markets. And one can show there exists an infinite number of equivalent martingale measures. And any one of those gives an arbitrage-free price for a derivative using risk-neutral valuation. Any one of those will give an arbitrage-free price. And what is the range of prices available? Well, this introduces the notion of super and sub-replication. And that'll determine the range of equivalent martingale measures. And the one that gives the largest price is the cost of super replicating. The one that gives the minimum price is the cost of sub-replication. And here, just to point out, it's the key insight, replication, which enables us to get a handle on this range of acceptable risk-neutral valuation prices. However, that's an infinite set, and the range is often too large to be of any practical use. And when that's the case, when the incompleteness is not, so that the range is too large, then we move to step 2 is, well, within this set, we need a rule for choosing an element, a unique element. And in the literature, there are basically 2 approaches. One is to specify an objective function with respect to the hedging error from using a partial replication. And an objective function could be a utility function. And then we're into what's called indifference pricing. And a second approach, which applies sometimes, if the hedging error is what we call idiosyncratic, then you can price, that uniquely defines the pricing measure, and you basically price ignoring the hedging error because it's non-price risk. The problem with these 2 approaches are that that specifying an objective function is often difficult, and the second approach doesn't apply. In my most recent research, which I'm going to put, this is sort of like a marketing pitch for, I have a new approach because I've been thinking about this problem for a while, how to price in an incomplete market. And it uses ideas from the mathematical notions of filtration reduction and just the fundamental theorems of asset pricing, but in 2 related markets. I give the reference here, SSRN, in case you're interested, but there's what I'm going to call the original market, and then I'm going to create a hypothetical market. And let me give you the idea underlying this new pricing method. A trader is looking at pricing a derivative, and they're thinking about synthetic replication, and they realize they can't exactly replicate the payoff. And they look at what payoffs they can replicate, and they decide this partial replication is the one that's important to me. So I'm going to hedge those risks exactly, and the remaining risks I'm only going to hedge on average. All right. Now, that partial synthetic replication determines an information set. A filtration reduction is what we call it. And a hypothetical complete market whose price processes are the conditional expectation under the statistical probability of the original price process, but given that filtration reduction. Now, in this hypothetical market with this new price process, it's complete. And there exists a unique equivalent martingale measure in this hypothetical market. Now, with one additional economic assumption, which we call a price consistency condition, this uniquely determines what we call an uplifted equivalent martingale measure in the original incomplete market. And this uplifted equivalent market measure can be used to price derivatives in the original incomplete market. So it's a different rule for determining which equivalent martingale measure is appropriate, and it's determined by the trader deciding which risks they want to hedge exactly and which risks they can only hedge on average. And we also know more that given a derivative in the original market, the partial replicating, well, the replicating portfolio in the hypothetical market for that derivative's payoffs can be used in the original market, and that'll give you the desired hedge. And it turns out that the value of the hedging error is 0 under this structure. And I'm hopeful that this approach can be used in practice because you don't have to specify an objective function. You only need to decide as a trader which risks you want to hedge exactly and which risks that you're going to hedge only on average. And it turns out it's a special case is the non-hedged risks being diversifiable. That's a special case of this methodology. I'm trying to move quickly, so I know I'm talking fast, but this is the last assumption modification extension that we need to discuss. And it's when markets are non-competitive. And I define a non-competitive market to be one where traders have a quantity impact on the price process. That is, they do not act as price takers. And there are two cases to think about in such a non-competitive market: when the quantity impact on the price is temporary or permanent. And in either case, this is a notion of liquidity risk, which can be characterized by a supply curve for buying and selling, which intuitively means that if you buy more, the price per share increases, right? And if you sell more, the price that you receive per share decreases, all right? And now let's talk about the two special cases when there's liquidity risk and we understand the supply curve. If there can be a temporary quantity impact, and by that I mean when you trade, you affect the price, but after your trade, the impact disappears, right? So it's only for your particular trade, and you do not affect the price process's evolution. And then again, with continuous trading, example, high frequency traders, one can show you can actually avoid these costs with the standard pricing methodology. So the standard pricing methodology will still approximately apply. Risk neutral valuation works. And as I say here, and I mentioned earlier, it's analogous to a variable transactions cost. The problematic one is if there's a permanent quantity impact on the price. And what do I mean by that? It means that after you trade, your trade affects the evolution of the price process for more, for a finite time period. Well, under this structure, traders can trade strategically and they can obtain manipulative profits, not in a, well, it could be a legal sense, but I'm doing it here more in a theoretical sense. And under this structure, the BMS methodology fails. All right, it's not like an incomplete market where we can still use risk neutral valuation, although we can't do synthetic replication, we can only do partial replication. Here, the methodology fails. And a simple example shows why. And the example is, suppose, let's look at a call option where an instant before the option matures and the stock price is just out of the money. Now, the BMS model will imply that the option is nearly worthless and the hedge ratio is near 0. All right, if a manipulator exists who can affect the underlying stock price, they can buy the stock an instant before it matures, push it in the money, and consequently, the true option value is worth the in the money value generated by the manipulator's trade. And the hedge ratio is 1 unity. All right, so just reflect. BMS, worthless option, hedge ratio 0, non-competitive market, the option has strictly positive value, hedge ratio 1, right? You couldn't be more different. The BMS methodology fails when we relax the competitive market hypothesis. Now, in theory, you could develop an option valuation approach in such a market, but you'd have to know the manipulator's trading strategy and their impact on the price. And in practice, such information is typically, it's actually almost always not available. All right, well, in conclusion, so the Black-Merton-Scholes methodology, technology is a seed from which a massive tree grew. And as I just discussed, my own view, and by the presentation, I've argued the Black-Merton-Scholes methodology is robust to modifying all of its assumptions using the key insight of synthetic replication, but one. And the Black-Merton-Scholes methodology fails when the competitive market assumption is violated and strategic trading exists that affects the price. Now, the good news is as a first approximation, most markets are not subject to such a violation of the competitive market assumption. And the competitive market assumption is a reasonable characterization of the market. And therefore, due to the robustness of the BMS methodology under the typical structures, it's my view, it is one of the most successful applications of economic theory to practice known to date. Whew. Okay, I'm going to stop there. I've been talking a mile a minute like a commercial sometimes, but I'm open for a few questions if there are any.
Thank you very much, Bob. Actually, there are some questions. So I'm going to start with Sanjay. Sanjay, you have a question?
Yeah, I've always had this question, Bob.
Sure.
HJM model was one of the most influential models in when I got my PhD. And there are two ways that one can fit the initial term structure. One is the time-dependent drifts, which are in the HJM models, which can even work with one factor. It doesn't need multiple factors. Or you can have just more state variables. You can have 3-4 factors, and you just have more parameters, and you can fit the entire yield curve. The advantage of maybe a multiple state variable model with stationary means, stationary drifts, which could be, which could have some state variable dependence, but they're stationary. They're just not like in Black-Merton-Scholes in your model and Thomas Hohenle model, they evolved just to fit the term structure. So what is your opinion, how it has evolved over the last 15, 20 years, like which direction to go? We can go like a multiple factor, a fine model, like, or
Right.
GM models.
Yeah, okay. So to answer your question, I have to refine your statement a little bit. So the model structures you're talking about are sometimes called finite factor models. And those you will often need to make one of the drift elements a function of time to fit an initial curve, all right? And my own view on those are that those approximations are okay, but I prefer an alternative. And the HJM model, actually, the initial forward rate curve is a state variable, right? So the entire curve is the state variable. So you don't have to fit it. You take that as a given, and then the evolution follows from that. And that was actually the motivation going way back to the creation of the HJM model. Now, special cases of HJM are those that you talked about. And the reason one might want to use those is because they generate very analytically tractable and estimatable versions of the general HJM approach. And of course, tractability, analytic tractability, computation, advantages, the ability to estimate parameters, well, are all useful in practice, okay? So I think that's a very, very nice special collection of submodels of HGM, but the HGM model actually, like I said, takes the initial curve as a state variable itself. And you can think of that Markov process, which is also a simple, which is also a special case, where the state variable is the curve, right? So long-winded answer to your question. I typically do that because I don't know how to answer questions with yes and no.
I think Hussein had a question, and we also have another question from the audience. So Hussein, do you want to go first, or?
Let me ask what's from the audience. So the question is it possible to find an optimal risk neutral probability in an incomplete market?
Well, so the answer is yes. I would not use the word optimal because there's no sense of optimizing over the set of measures, but there are different rules for selecting an element from the set of equivalent martingale measures. You can do it based on an objective function, and there you would choose the personalized valuation measure determined by a portfolio optimization problem. You could say, I want to minimize the sum of squared errors, and that'll determine a unique probability measure. Or you could use what I talked about as my alternative approach, which I would call a consistent uplifted measure. But I don't think of it as choosing an optimal one. I think of choosing one that satisfies economically reasonable conditions that you as the user of the method feel comfortable with.
So I was going to suggest maybe we take a little break because we didn't take a break before, after the last talk. So what do you think, Hussein? Do you want to ask a question, or we break for 15 minutes?
Yeah, I had a quick question actually, going back to the model or the approach that Bob discussed about the risks that you hedge and the one that you hedge on average.
Yes.
So what is the role of the market price of risk in deciding which one to hedge and which one to hedge on average?
Right.
So
yeah. So the ones that you hedge exactly, there are risk premium for. All right, and that's embedded in the choice of the equivalent martingale measure. The ones that you hedge only on average, they're basically, there's no price, there's no risk premium. And so they're priced under the statistical probability measure. All right, so the idea is that you feel that you don't need a risk premium for those because you're comfortable bearing those risks. But the risks that you don't want to bear, those are the ones that you exactly hedge. There are market prices of risk for those.
All right, thank you.
You're welcome.
Thank you so much. Thank you, Bob. Wonderful
you're welcome.
Presentation and the overview of all the things that happened, and of course some new work of your own. We appreciate it so much.
Thank you, Bob. So we'll take maybe a 3-minute break if people